attendees, and any registered attendee unable to join today will have a link to the recordings. For today's schedule, I'll do a quick introduction to ASD, and then we'll get into the presentations. At noon, or at the conclusion of Dr. Redinger's presentation, we will serve lunch in the conference room to the left as you exit the auditorium. And the next presentation will start at 1 p.m. and then we'll take a quick coffee break around 2. So once all the keynote speakers have presented, we will conclude the event for the day and take any questions you would like out in the hall. As any event that incorporates multiple speakers, we may experience challenges with the integration of presentation formats or other technical issues as you've already seen today. So please bear with us while we address them so we can start promptly after the issues are resolved. And so let's get started. Who is ASD? ASD was founded by two renowned remote sensing scientists, Dr. Alexander Getz and Dr. Brian Curtis. And Brian's actually a speaker presenting here today. They established ASD to address a fundamental need of earth science researchers to have a robust, high-performance, portable instrument that could be used in fieldwork. Our organization specializes in near-infrared technology used for material identification and analysis. ASD, or analytical spectral devices, was incorporated in Boulder, Colorado, where we currently have our headquarters. We also have a large remote presence with sales representatives, agents, and distribution partners located all over the world. ASD is now a Panalytical company. This was effective in July of 2013. Panalytical has expertise in leadership in X-ray instrumentation and services. Their goal was to add ASD's expertise and leadership in NIR spectroscopy to create a combination for a full spectrum of measurement solutions from one global manufacturing and service organization. With over 3,000 instruments in over 70 countries, there's a global presence of researchers using ASD instruments. And we are videotaping today's events in order to share these presentations with many of our interested out-of-country registrants. Today, ASD is innovating and addressing customer needs by providing the latest technologies combined with the highest standards of quality and measurement. We continue to provide customers with value-enhancing solutions to their material measurement needs by offering resources of instrumentation for field, nearline, and online material measurements, application expertise supplied by our Cal Solutions team, and service and support for installation and post-sale support worldwide, including service centers in the Netherlands, Brazil, China, and soon Australia. ASD instrument lines include FieldSpec for remote sensing and field research work, the TerraSpec line for mining and exploration production, the Quality Spec line for online and nearline process control, and the Lab Spec for material inspection and identification in the field and lab. ASD offers several spectroscopy software options for our customers. Our in-house spectrometer software includes data acquisition and analysis tools for remote sensing and industrial applications. Third-party software options include those for mineral analysis, data processing, and chemometric modeling. We offer a comprehensive variety of accessories, such as our contact probes, to meet a multitude of application requirements. Please visit our product section on our website at asdi.com if you'd like to learn more, or you can ask me as we have time today. And now, please allow me to introduce Dr. Brian Curtis. Dr. Curtis is one of the founders of ASD and currently serves as ASD's Chief Technical Officer. He has over 30 years of experience in the fields of geology, spectroscopy, and optical remote sensing. He received his bachelor's degree in Earth and Planetary Sciences from Washington University in St. Louis, and his Masters and Ph.D. in Geochemistry from the University of Washington. His post-doctoral research was at CalTech, where he assisted in the development of field-portable spectroscopic instrumentation. Prior to joining ASD, he held a research faculty position at the University of Colorado in Boulder, and in his current position, Dr. Curtis applies his experience to a diverse range of analytical problems in the area of remote sensing and natural resources. Brian will now be presenting on a new release of ASD, the FieldSpec Dual Collection Software System. Right?
Oh, I need to go. Okay.
So here's where we appreciate your patience.
Well, just get rid of that and it's in this folder. Oh. There we go. So I'm just going to give also a little history about software that allows use of two spectrometers at once. And the main problem is making field measurements on days that have less than ideal conditions. On days where you don't have perfect blue sky horizon to horizon, you have conditions where the light level at any given point in the ground is changing with time. And even on days when there aren't clouds in the sky, you can still have time-varying water vapor, which changes the solar irradiance as a function of time. And when you normally make measurements in the field with a single instrument, you're measuring, say, a white reference panel at some time, and then at some time later you're measuring a sample. And what you're doing is making two radiance measurements and then ratioing those to get reflectance. And inherent in that is the assumption that the irradiance hasn't changed between those two measurements. And clearly, if you've got certainly conditions like in this photograph, or even on a day where there's just slight time-varying water vapor, that isn't true. And so what you end up with is a reflectance spectrum that has a bias in it that's related to the change in irradiance between the time you measured the white reference and the sample. So what this means is that typically people wait for these kind of perfect days or golden days to make their field measurements. And that really limits the number of days when you can perform field work. Typically, for a lot of, especially if you're trying to do field work here in the Northeast, you might allocate 2 or 3 weeks to do field work. You're making other measurements on many of the days, and you're hoping for that one perfect golden day where you're out running around as fast as you can collecting spectra, because that's the day. So if you have two spectrometers, you can hook them up together. Back in the early days, we would do this by building the two spectrometers into the box. But these days, you can use wireless networks to allow one computer to talk to two instruments. One of the things that has been shown to be really important anytime you do this, though, is that you really have to intercalibrate the two instruments, both on the X scale and the Y scale, because if you don't, all kinds of errors creep in. And I'll talk a bit more about that later on. But the real key here is to be able to collect near simultaneous radiance measurements of both your reference panel and the target. This doesn't take care of the other part, which is distance. Because the irradiance at any point varies not just with time, but if you are measuring your white reference in a different location than your sample, you've got that to deal with as well. But certainly, in many cases, the time varying component is dominant. And then lastly, and this is really more of a convenience, if you can process and display the data in real time, give feedback to the person making the measurement, then in fact the data you're collecting is good and of high quality, as opposed to finding out later on. So a little history. The first dual instrument that ASD made was back in 1996. And it was actually, there were non-commercial versions quite a few years before that. We, in the early 90s, in I think 93 to 95, had a couple of kind of research instrument development grants from NASA and the Corps of Engineers to make dual spectrometer systems that just covered the Wiener range, so 350 to around 1,000 nanometers. And these systems were for kind of special cases The instrument for the Corps of Engineers was for the Cold Regions Research Lab in New Hampshire, and their application was measuring sea ice optical properties. And the way they had been doing it is they would measure the irradiance above the ice. They would take that sensor, put it below the ice, measure the irradiance again, and from the ratio of those two, get the transmission of the floating sea ice. Again, that would only work when irradiance was stable. So they had a lot of days where they'd go out and they couldn't make measurements. So we designed a system that, again, had two silicon array spectrometers that allowed them to simultaneously measure those two light fields. We did for NASA, it was for the CWIS program. This was pre-launch, but it was an underwater instrument that was in a pressure vessel that also had two spectrometers, one that was measuring downwelling irradiance and the other one was measuring upwelling radiance, and it was built into a pressure vessel, and they could this was lowered to the water column, then measured the upwelling radiance and the downwelling irradiance as a function of depth. And they used that to calculate water-leaving radiance. And during that time, there were some NASA researchers that developed some algorithms to derive water-leaving radiance from above-water measurements. But again, those measurements required measurements of the radiance reflected off the water, the radiance from the sky, simultaneously again, because again, when you're out on a ship and you get to each of the stations where they're going to make measurements, you have a certain amount of time, and you can't wait around for a perfect blue sky day. You have to make measurements on whatever the conditions are. So we ended up kind of commercializing the instrument designs that were done for that research into the first FieldSpec dual, and that was in 1996. And then when we came up with the FieldSpec Pro in 2001, we kind of carried that over. This is a picture of that instrument. You can see the two fiber optic cables coming out there. Now, those instruments were used primarily for ocean color research. And there are a little over 100 papers out that kind of reference these instruments. Back then, we didn't do a very sophisticated intercalibration of the wavelength scale. What we used is you could look at the oxygen line, which is a nice sharp line in the solar spectrum, and if you ratio the radiance of the two instruments, and those are out of calibration, what you would see is a little like a sync function because those were offset from one another. And so you would manually, there was a way in there where you could put a manual offset into one of the spectrometers to get that, to kind of minimize or null out that feature. And that's how you did the wavelength calibration. But unfortunately, by 2006, when we came out with the FieldSpec 3 series, the kind of interest level in the FieldSpec dual had dipped down, and we were building maybe one a year, and it was decided that we wouldn't carry that forward. So since 2006, ASD hasn't had a dual spectrometer instrument. Yet there's been a lot of interest in it, because certainly the land-based community really wanted a dual capability at over the full wavelength range. There was a paper that came out in 2012 that the author, Chip author, that developed a kind of workflow for collecting matched spectra on two systems, one fixed looking at a white reference and the second one that could move around, and did a lot of modeling of the kind of errors you get when you don't properly intercalibrate the X and Y scale. At the bottom are some graphs showing the if you have a feature, these are modeled spectra, but if you have a feature like this, and everything lined up right in the wavelength scale, they ratio out very nicely. But if they're offset relative to one another, you get a feature that looks something like this. And this is, in fact, what we use to manually make the adjustment back in the early days. And that's, if you go back and look at the earlier versions that have been done, you know, this early solution, it was Wiener only, didn't go out beyond 1,000 nanometers. And a lot of that was, you know, partially that was based on cost. I mean, to actually build an instrument that had 2 full-range spectrometers in it starts to get really expensive. It was, you know, focused on water measurements, and it only had this manual method of wavelength intercalibration. And then, you know, there have been a number of groups that have done manual systems for doing the dual spectrometer. When you're manually collecting the data like that, they're not perfectly time synchronized. You get the time difference down to about a second. It does allow you to fix one unit while the other one moves around, but it does, you know, you don't see the reflectance spectra until after the fact, so you don't have feedback in the field. And because, you know, there's no easy way really to intercalibrate the two spectrometers. So this is software we finished up just very recently that automates this whole process, and it covers the full wavelength range. And one of the things, besides you know, seeing the paper come out that shows that this would work, we also realized that there's a large install base of our instruments out there, and if we could do a software solution, people wouldn't have to buy a new instrument to do this. They would just need to get 2 instruments together, and as long as they had similar wavelength spectral resolution profiles, you could use them together. So the software does this intercalibration of both the wavelength scale and also the radian scale, and because they're linked together, you can get down to a synchronization that's about equivalent to a single scan, which is around 100 milliseconds. They're using wireless communication, so one of the spectrometers is hooked to the laptop using hardwired Ethernet, and then the other one is connected with Wi-Fi. And then that also means you can display, because the software is talking to both. You can compute and display a reflectance spectrum. This is kind of what the system looks like out in the field, with one of the units kind of attached to a tripod, and it's set up so that it's continually viewing this spectral on white reference panel. So besides intercalibrating the X and Y scale, the other issue that you have to deal with is that the resolution of the instruments has to be equivalent, because if you have 2 instruments that have significantly different spectral resolution, when you ratio the spectra, you get artifacts here. If these were the same resolution, you just get a line of 1. And here you can see this is an example of a section of spectrum of Mylar, just from 2100 to 2200 nanometers, so a fairly small region. These are fairly sharp features. You can see 2 things that happen as you change the resolution. Obviously, the depth of the feature gets shallower as you reduce the resolution, but also the position of the feature shifts. Anytime you have a asymmetric absorption feature, the wavelength of the absorption, or the reflectance minimum here, is dependent on spectral resolution. And the more asymmetric it is, the larger the shift. This is part of the difficulty of what people use for wavelength calibration. Because if you use a reflective material like rare earths or things like that, the wavelength of those features is dependent on resolution. So it's not a single value. So one of the things that ASD wrestled with about, I guess it was about 8 years ago now, was that if you want to do a lot of things with a spectrometer, like the quantitative analysis and such, and you want to be able to take a calibration that's done on one spectrometer and move it to another one, they really need to be relatively matched to one another. The resolution as a function of wavelength needs to be very similar from one unit to the next. And really prior to 2007, we had specifications for instruments. So let's say a FieldSpec standard resolution had a specification for 10 nanometer resolution, but when you were building the instrument, you would, the instrument would get focused, the grading, would do all the alignment, the focusing of the optical elements. And if we got higher than 10 nanometers, that was okay. It was always sort of a one-sided specification. It had to be 10 nanometers or better in order to pass the spec. The problem with that is you ended up making instruments that the resolution profile, while it met the spec, it could be better than the spec, because from sort of the remote sensing, the more spectral resolution is better. But if you're trying to use instruments, multiple instruments for the same application, what you really don't want is every one as good as it can be. You want everything to be the same. So we put in place a program to have specifications both on the high and low side, and also a specification at many different wavelengths, so that the profile of the spectral resolution was very constant from machine to machine. And we also changed the way that changed the ways we did wavelength calibration. Prior to 2007, we used a monochromator that was calibrated to a laser line. But the problem, again, with the monochromator is that in order to get enough light through the monochromator, you have to be allowing a fairly significant peak width through, and there's some uncertainty. There's more uncertainty in the wavelength of your calibration source. So we developed basically a box that had a number of atomic emission line sources in it and we designed our own lamps to get enough intensity, because kind of the standard sort of pen ray lamp that you can get from, say, an optics catalog, particularly at the longer wavelengths, it didn't put out enough energy to get a good signal to noise in the lines. So this allowed us to do our calibrations using emission lines, which are, from the standpoint of our spectrometers, are infinitely narrow lines, because they're well under any kind of resolution that we're in more in the 5 to 10 nanometer range. So it really improved the accuracy of the wavelength scale calibration. And then we built a lot of jigs and fixtures that we use, so we could watch those lines and tune the spectrometer to match the resolution profile that we're targeting. And all this means that it ends up that if you get two FieldSpec standard resolution images together, they're going to match each other quite closely. Here's another example of why you want to align the spectral resolution scale very closely. Here's a solar spectrum with all its sharp features in it. If you just offset a little bit in ratio, you get all these spikes, which would be, so if you had two spectrometers you were using together, you really need quite precise wavelength scale intercalibration in order to get a reasonable result. So what we ended up with for this system was we still use the atomic emission lines to calibrate the individual spectrometers, but in the field, right before you make your field measurements, you view this, it's a reference tile that has a glaze that has a mix of a couple different rare earth oxides in it, and then it also has a piece of mylar at the top. We need the mylar because the mylar gives us a few sharp features out here where the rare earths don't have very many features. Now, we're not relying on this in any way for any kind of absolute calibration, really just a relative. So we view it with both instruments. One of the instruments gets designated as the master, and then we do a fit of one set of peaks on the one instrument to the other one, and then we just do a slope and offset correction to the wavelength calibration of that instrument to line the two up. So here's an example. The red dots are what it looked like of the wavelength calibration mismatch between the two spectrometers looked like before we applied the slope and offset correction. And then the green, and this is an average, this was I think about 60 different intercalibrations. So that the red is the average difference between the mobile unit and the fixed, what we call the fixed base unit. And then the green is the amount of difference in wavelength calibration, again, at these wavelengths, after we did the slope and offset. We decided to use the slope and offset because we back in 2007 did an interesting experiment where we just put a spectrometer in the back of one of the employees' cars and drove it down these four-wheel drive dirt roads, and the whole idea was to let it bounce around a bit and see how the wave, what the characteristics of the drift in wavelength calibration were on a typical instrument. And we found that a slope and offset was enough to kind of correct for around 95% of the shift that we saw. So here's an example of how the whole system works. We used these two FieldSpec 4 instruments. The software also works with the older FieldSpec 3s. When we did this, the FieldSpec 3 line started before 2007 when we put in place a lot of these new manufacturing techniques. So early FieldSpec 3s probably should get kind of brought up to the current rev before, just to make sure you get the best performance out of it. But anyway, this test we used two FieldSpec 4s. We used this one here for the fixed base unit, but it's the one that stays still and monitors the white reference. And then this other one here for the mobile unit, the one that moves around. And this is I went back and looked at the irradiance, or just the radiance coming off the white reference panel, and looked at how the light conditions were changing during the about 30 minutes that we were making measurements, a little less, closer to 25 minutes, I guess. And for water vapor, what I did is I just took a ratio to get the depth of the water band feature, one of the ones near, I think near about 1200 or so. And you can see the amount of water vapor was changing quite dramatically. And the brightness, overall brightness, was just integrated over the whole spectrum. And the brightness didn't change as much as the water vapor did. So when you're out in the field, we built this fixture that allows you to mount the pistol grips holding the fiber optics of both instruments, so that both instruments are viewing roughly the same patch of real estate on the white reference panel. And the mount's designed so that these holders slide in, so depending whether you've got the round Spectralon or the 5x5 or the 10x10, they all kind of fit on here. So you start out by both viewing the white reference. You collect the white reference. Then they both view this is the wavelength standard or reference file. And again, this is only used for intercalibration. It's not used in any absolute sense. This is sort of the setup you would do if you had a reasonably good day with, not perfect day, but because here you're making the assumption the light hasn't changed that much between collecting the white reference and collecting the wavelength reference. And we tried this on a number of days where, even if the light is changing enough, it doesn't change the wavelengths of these positions, so that this works relatively well. If you want to be more careful about it, you can use, a lot of the systems have this, it's called a contact probe that has a light source built in. And if you don't want to worry about light conditions for the wavelength scale intercalibration, you do get a little better results by using the contact probe to make again, you'd have to move the fiber optic of the two instruments back and forth. So you make the wavelength measurement using that accessory. But then, once it's done this, the software takes the two scans, calculates peak positions, does the regression to find the correction, applies the correction, and then gives you some statistics back as to, how good a job it did matching the two instruments. Once you've done that, you go back to doing the Radians intercalibration, where again both instruments are viewing the same white reference panel. And the thing is, if you assume that the Radians calibration of the instruments was perfect, you could just go and collect Radian spectra, ratio them to get reflectance. The reality is that there isn't, they aren't perfect. So by collecting this, by having both instruments view a white reference panel simultaneously, you get a ratio of what each instrument thinks the radiance is, and you can use that as then a correction factor to correct subsequent measurements. So this is, we call this the time zero radiance ratio. And what we found is that you do this when you start up at the beginning of the day, but probably once every 20 minutes or half an hour. It's not a bad idea to go back and do this every once in a while if you want everything to be as tight as possible. So once you've done those things, then at that point you can move around in the field and collect spectra. And this instrument, the laptop controlling this instrument, is continually polling this one to get the downwelling radiance, or the reflected radiance measurement, the fixed unit. And then it's just doing the computation that it takes the instantaneous ratio between the radiance measured from the mobile unit divided by the fixed unit, and then it corrects it using this factor that it measured at time zero. And again, this all takes care of any time-varying irradiance, but depending on conditions, the distance between this person and this tripod can also be an issue. So you just have to be aware of that. So here's some examples of spectra that were collected. This has been blanked out in the deep water features. But you can see that these were collected on a day when, it looked pretty crummy. There was a lot of cirrus clouds drifting in front of the sun. And what we found is that, if you've got thick clouds, while you can make measurements when the sun is behind those clouds, the energy level is so low, you do get noise creeping into the spectra because of just low levels of irradiance. But as long as you've got space, as long as you kind of limit your collection to the time when the clouds are kind of away from the sun, this does do a very good job of taking care of all the time-varying water vapor that you typically encounter in the field. So just in summary, the software, it provides the means to accurately intercalibrate both the reflectance scale and the radiance scale of the two spectrometers, synchronizes the collection on the two to within a tenth of a second or so, and it really enables collection of field spectra under conditions that normally you wouldn't try to make measurements. And separating the collection of the white reference and sample scans does enable some interesting things. Certainly for goniometers, where if you want to turn those into reflectance, having one instrument just sitting there measuring a white panel while the other one is transiting and measuring different angles is useful. We've had a couple people that have been interested in drones. The idea that, like in a field trial for crops where you have 50 or so sites in a field, being able to set up your unit measuring the white reference panel adjacent to the row, and then just using a drone to hover over each of the field sites and rapidly collect the upwelling radiance values is an interesting application that we may be trying to test out this summer. And then a lot of people using tractor-mounted systems that have an instrument on a boom looking down at a tractor. Again, having a separate instrument measuring white reference is useful. So for, again, I mentioned compatible systems. The FieldSpec 3, that project we called the Summit Project. This was back in 2007 when we changed a lot of the manufacturing approaches. So any instrument, either these serial numbers or this one and above, are would be, are compatible with the software, then all of the FieldSpec boards. The key is you want them accurately calibrated, and they need to be at the same resolution. So we have a lot of different flavors. You wouldn't want to mix, say, a standard res instrument and a high res instrument. They would probably be the same. And we have done trials where we mixed FieldSpec 4s and FieldSpec 5, FieldSpec 3s, and that works fine as well. So that's it. So, any questions? Seconds.
All right.
Thanks, Brian.
Yeah. Back to this one.